record. There we go. Well, I want to go ahead and get started here. So my intention here is to go over what's labeled in your handouts as hands-on problem 5. And this is essentially a simplification of the example I went over in the last lecture. So we're going to be looking at a longitudinal dose response model that we're going to use. We're going to apply it to analyze some longitudinal summary data, both some sample means as well as sample standard deviations. And in this case, it's going to be then a model-based meta-analysis of some ADAS-Cog data in Alzheimer's patients, and we're going to look at the ADAS-Cog as a function of both time and donepezil dose. So we're just going to be focusing on one particular drug in this instance. So we've got some post-baseline sample means and sample variances for ADAS-Cog change from baseline. And we've got that for a number of doses of donepezil, hopefully enough to characterize a dose response. The data set is actually, if you wanted to see the larger data set, which includes some additional drugs, that's available on opendiseasemodels.org. So we're going to be looking at the results from 12 studies containing 24 different treatment arms. And you can see it corresponds to about 180 sample means, 80 some sample variances, and those all are collectively correspond to results from over 2,500 patients. But of course, we're only going to be looking at the sample statistics. So the mission you had was to construct a model for ADAS-Cog change from baseline as a function of donepezil dose and time. The data set you'll find there is under the name donepezil ADASdata.csv, and this is all inside a folder called ADAS-Cog hands-on. We'll go ahead and pop over to that here. So actually you'll see that I've got a few additional files here, but the key files here within ADAS-Cog hands-on is, of course, the data. Sorry, where the data? There we go. The data set. I'm going to go ahead and open that up. Okay, and it's got a number of things in here. I won't go through the definition of all the columns in here, but the critical things in here are going to be things like the which drug that we're talking about. Where do we go? Here's our ADAS actually represents ADAS-Cog change from baseline. We'll be using N-treat is going to be the sample size we're interested in. By the way, if you do want the definitions for all these, I believe there is a data set definitions file available on Open Disease Models. At least I hope there is. Then there's various covariates here. You've got things like age, baseline MMSE, which is another measure of Alzheimer's disease severity. And finally, the other thing that we're going to be using here, somewhere in there it had to be time. Where'd time go? Okay, there we go, week. So it's in terms of weeks. And down here, yeah, the standard deviation. Yeah, and let's see. Yeah, okay. I'm trying to remember this one. I think I may have actually derived from things that were reported in other columns here. But those are the key elements we're going to be making use of. Push that out of the way. So we're going to want to model that. It's worth taking a look at what the data is looking like. If you wanted to, there's an R script in here that just creates a couple of simple plots here. Let's just go ahead and take a look at the plots. So this is giving you some idea. We're looking at the mean ADAS-Cog change from baseline for the various trials here. You can see in the legend here, we're looking at some different doses. So these all correspond to daily doses of donepezil. So you've got 1, 3, 5, and 10 milligrams per day, as well as placebo arms. In here, we've got a number of somewhat shorter trials, some as short as 12 weeks. Here we've got one that looks like it must be 6 months here. But then we've also got some very long ones that go out to about 3 years, right down here in the donepezil 10s. So that's the data we're going to be working with in terms of the sample means. And let's see, this is our sample standard deviations in here. And a few weird looking things like this one. I have no idea why it's doing that sort of odd bit. Oops, pushing the wrong buttons here. We don't need that. Okay. Okay, so that's what we're going to be working with. And let's take a look at the further specifications of the problem here. Oh, I forgot I had actually had those. These are the same pictures we were just looking at. Okay, so the model is a simplification of the one I went over during the lecture. And the key elements, key simplifying assumptions here is I'm no longer using t-distributions for some of the inter-individual variation, and I've simplified the placebo effect to essentially just a constant placebo effect. So otherwise, the model is essentially the same as we were looking at before. So I've got here the delta ADAS here just refers to ADAS cog change from baseline in the, let's see, it's the ith occasion and the jth patient in the case study. So as we started out developing a model before, we start out by constructing our model based upon what we believe a suitable model is for individual patient data, and then we will modify that appropriately to describe the sample statistics. So for our individual patient data model, we've got, in this case, it's just going to be normal for our change from baseline. And I've allowed for some inter-trial variation in the residual variance here. Our basic model for our conditional mean here is we've got a disease progression component here that's just being described as a straight line over time. So we've got some parameter alpha jk that has possibly both individual and intertrial variation. And then we have our observation time, our tijk. We have a placebo effect and a drug effect component. So these are being treated as additive in this case. This is just, it's probably notational overkill, but this is just here where I sub placebo JK is a sort of a placeholder so that the e-drug thing gets zeroed out in the case where it's placebo. Actually, the more I think about it, it's unnecessary, because if I calculated e-drug for placebo, DJK would be 0 and it would go away anyway. Anyway, that's overkill. We could lose that. In fact, we can just cross that out. Okay, so let me jump to the e-placebo. For e-placebo, I'm just going to have that actually just be a constant. So that's something that takes on a non-zero value for, or possibly non-zero for post-baseline observations. And it's just described here as a constant with, which is our, let's see which one, yeah, our e placebo. Actually, I should probably, start down here with the first one where so I've got the e placebo JK, which is the value specific to both study and individual, has a normally distributed inter-individual variation, but it's about a mean here which reflects inter-trial variation, as shown down here, this e-placebo study K component here. So we've got normally distributed both inter-trial and inter-individual variation. in here, but that describes our placebo effect instead of using a Bateman function like we did in the previous example. And then for the drug effect, the effective exposure, the expected dose, is described as essentially just an exponential type function. So we basically got dose raised to the gamma. That's normalized by a reference dose. We probably didn't really need to do that in this particular case, but about the only rationale for doing that is when we do that, this E delta here on this side will represent the essentially the steady state drug effect associated with a 5 milligram per day dose of donepezil. Okay, so we've got D over D ref raised to the gamma. So that's the dose response component, but then we also have a component which allows for the fact that the drug effect does not come on instantly, but takes some time to develop. And in this case, it's using a Emacs style function to describe that onset over time. So E delta would then be the steady state effect. And this ET50 you can think of as being the time at which the response is half maximal. And in these, in E-drug, the only part with any unexplained variability is going to be this E delta K, which is allowing for some inter-trial variation in that, but no inter-individual variation. And that is described, here it is, E delta K. So that's just being described as normally distributed inter-trial variation. And what are we missing? Oh, I guess I never described the slope, which is down here, which has both inter-individual as well as inter-trial variation in that. And then finally, we've got the residual variance term here, which also has some inter-trial variation. So it's the variance is inverse gamma, or equivalently 1 over the variance is gamma distributed. And so this is set up in such a way that this gamma distribution has a mean of sigma hat squared. And I couldn't tell you just off the top of my head what the variance is. Should be able to. Trying to remember gamma. I think gamma is alpha over beta squared, though I won't swear to that. Where was I going with this? Oh, actually, I was saying it the wrong way. No, I'm sorry. I was right the first time. I can't remember what the variance off the top of my head of the gamma is. That's one way of doing it. Another way that I've commonly used is, instead of doing it in terms of a gamma distribution, is actually to have the standard deviation take on a log normal distribution, and that tends to work reasonably well, and it's actually not grossly different from what you end up with a gamma. Okay, so that's the model we're going to be using. Now, again, this is our individual patient data. Now we have to modify it to be descriptive of what we're doing for our aggregate data, our summary statistics. So, and those summary statistics are going to be the sample means as well as the sample variance data. And so for a sample mean, it's relatively simple modification for that portion, for the residual variation component, since that's just going to be our function for the conditional mean for the ADAS-Cog change from baseline. And then it's a variance made up of essentially our individual variance component divided by the sample size. And just to follow through on that before we talk about the sample variance, the other changes that are needed is for since we're no longer talking in terms of modeling individuals, we're talking about modeling treatment arms. We still have some within arm correlation that we account for by describing some inter-arm variation. But because our arms are not really created equal. They're made up of different numbers of patients. The main adjustment for that is it's the same model as our inter-individual random variation model, except that we modify the variance term by adjusting for sample size. So that's true for both of these parameters. And finally, for the inter-trial variation, there is no need for that kind of a modification. Okay, so if we were only doing the means, that would take care of what we're going to do. And then if we're also going to model our sample variance terms, then we're going to model that as gamma with the parameters as you see on the right. So we've got our n minus 1 over 2 for the first parameter and n minus 1 over 2 sigma squared marginal. So we've got this marginal variance term. And if you go back and use the derivation strategy described in the lecture, what you end up with for our case here is we end up with first of all, we end up with a term where we end up with times squared times this omega alpha squared. So we've got actually the inter-individual variance component comes into play here. We also end up with the variance term squared, our variance term for the placebo, and then finally our residual variance component, all contributing to this sigma squared marginal. And that all gets stuffed back into here. Okay, so now if you did as I suggested at the end of last lecture, I suggested perhaps you take a shot at this first, just modeling the mean. And if you did that, you wouldn't have to deal with the complication introduced here. And so you can go ahead and start the problem that way. And then you have to do the additional calculations. And if you're going to bring in the sample variance terms, I'll be honest, I haven't actually done that exercise to compare the results you get for the two cases. My suspicion is you're probably not going to see large differences between the models. The place where I suspect you're most likely to encounter differences is going to be in modeling the inter-trial variation and the residual variance component. That's the part that's most likely to change when you introduce the additional data. Let's see, okay. So let's go ahead and take a look at, see what it looks like to actually do it. Let's just get that out of the way here. I believe I've already got it open. Yep. Oh, but let's pull up the model. Oops, actually I opened it with the wrong instance of Aquamax here. Let's do that again. That's better. Okay, so let's take a look at the model. Actually, I wanted to bring up the, see if we can bring up pieces of the slide while we're at it. Can I get rid of this guy here? Okay, just wanted to have some of that visible here. So, okay, so let's go ahead and implement some of the pieces here. So the first part here, just looking at the ADAS-COG change from baseline, I've used the name ADAS-CFB inside the BUGS model, and that corresponds to the delta ADAS in the slide. So we can see we've implemented this normal here with the sample size adjusted variance right here. So it's D norm CFB mean is our first parameter. Tau is our second, where tau is calculated right down here, where I've got tau is going to be tau study, meaning this is going to be a study-specific value of tau because we've modeled intertrial variation in that, times the sample size, NPAT, meaning number of patients corresponding to that particular observation. So tau study then, as I say, is a study-specific value of our residual variance term, and that's being generated up in another loop. So if we go up into here where I'm looping over studies, in particular, you'll see a line right here where you can see tau study is gamma distributed with a couple of parameters here called A resid and B resid. Those two parameters correspond to, let's see, I probably have to scroll up to the previous slide. Those correspond to the two parameters you see here in the gamma distribution that I symbolize here as what alpha sigma and alpha sigma times sigma hat squared. And if you want to see where those are generated, that's actually generated down, I believe, where we're dealing with constructing the priors. So that's all happening right down here, where I've put a prior on that A resid term, which corresponds to the alpha sub gamma in the slides. And then somewhere else here, we should have, okay, here we go. Here's our sigma, our residual standard deviation. And here I've calculated the corresponding precision value for that. And so you can see where that finally all goes together to calculate this B resid term. So this A resid and B resid, again, are nothing more than what you see on the slide here for the parameters to this gamma distribution. Okay, back up here. And then we've got, let's ignore the variance for the moment here. There are ADAS CSV here. The mean is going to involve our progression component. So we've got our arm-specific slope here. Just remind you, I did the same thing I did in the example before. I used the word unit instead of arm here. That was an attempt to use a somewhat ambiguous name so that when we start combining individuals and summary data in the same thing, we're going to use the word unit to refer either to an arm or to a individual patient, depending upon the context. So in this case, unit is referring to a treatment arm. So we've got our arm-specific value of alpha multiplying time, then our placebo component here, and our drug effect. And here we've got our drug effect being calculated. So it's just we've got that, the dose effect component. So the D over D ref raised to a power, and then our Emax function of time here. And I've kind of danced quickly past some of these things that we've used before for hierarchical models, but you can see for any parameters that have either inter-trial or inter-arm variation, you'll see the nested indexes showing up here. So we've got alpha, which has both inter-trial and inter-arm variation being represented by its arm-specific value, and then you've got the nested index here pulling out the appropriate value for the arm associated with the ICE observation. Same thing for this E placebo term. Notice in the case of this E delta, it only has inter-trial variation, so it's only pulling out a trial or a study specific value here. So this still using nested indexes, but pulling out a study specific instead of an arm specific value. Let's see, what more do I want to point out? We pointed out the residual variance term in here. Okay, so that's most of the core. Just go back up here and point out where we have the process is going on here for things that have where are we going? Let's start with the ones that have inter-arm variation here. So I've got a loop going over arms, or as I call them here, units. So we've got for example, the E placebo value. It's normal, centered about a study specific value for E placebo. And so you can see again, we've got a nested index here to pull out in this case, it's to pull out uh, the indicator, the index for the study corresponding to the ith treatment arm, not to be confused with the ith observation in this instance. In this E placebo study is generated up in this previous loop that's going over studies. So you can see this E placebo study, again, normal. So you can see this cascading process where, you sort of start from I guess you can sort of think of it as the outer loop and work your way in. So you have to generate the study specific value, which then becomes the mean for the arm specific value. And the same thing is happening for our alpha here, our slope value. Okay, some of these are also, okay, I see. This is just for the fact that, recall, we have to have a sample size adjustment for the inter-arm variation, and so that's what's going on with these two lines, which is appropriately adjusting the inter-arm variance for the sample size. And I go through these steps both for, this is the values here that I've highlighted are the ones that are going to contribute to the likelihood. The values here with the modifier pred are going to contribute to a simulation for our so-called population simulations. Same thing happens above here for our intertrial variation. And the one additional thing that's different on our intertrial is we do have a couple parameters that have only intertrial and no interarm variation. That was, for example, the residual variance component, and where's E delta? Here we go, and the steady state drug effect component. Let's see, which should I mention next? Okay, why don't we go ahead and, oh no, maybe before I introduce what we're doing to bring in the sample variances, other things that were done here is that Emax component, that Emax function of time. I did use the truncated Emax parameterization for that, like we've done in previous examples, to try and reduce some of the autocorrelation. I'm trying to remember if I ever tried this particular example without it. Probably not. I think I tried the fuller example that I used to demonstrate in class, but not this one. But with Emacs style models, it's generally a good idea to take a look at that as an option. Let's see. Most of the rest of this is just a straight reflection of the proposed priors. Actually, did I propose the priors in here? I guess I never actually did. Since I did not, oh, that was very clever, excuse me. Since I didn't propose priors, I guess that's something you'd have to think about. As you can see in here, I used for the various standard deviations in here, which I called omegas for the intertrial and interstudy here, I used a fairly wide uniform distribution for those. Yeah, ditto for the residual component on there. Also for that additional gamma parameter in here. And then let's see, we've got a couple others for that B parameter. I used the uniform, and just to, I guess, illustrate another option that you can consider when I'm trying to restrict something to be non-negative. The choices I tend to think about as possible approaches to use for a prior in the case where, let's say in particular for the case where I want them to be pretty weakly informative. The choices that usually come to mind is a uniform that starts at 0 and goes to some relatively large number, outside the range, well outside the range at which I think is reasonable, or to use a log normal. Or another option is the one I show here, which is to use a half normal. So where I've used the I modifier, in this case to represent a truncated distribution rather than to represent a censoring. Now technically that modifier, the I modifier, is designed only to be used for censoring, but it's okay to use to construct a truncated distribution in the special case where the parameters of the distribution it's modifying are not random variables. So as long as these quantities are constants, that's an appropriate way of constructing a truncated distribution. If either one of them are random variables, it's not appropriate and will not work correctly. Okay, what else do I need to tell you? Okay, that's the core bits there. Then I guess the one last bit is now introducing the components for, sorry for the scrolling, there we go, for modeling the sample variance, and that's right here. So we've got our variance, our observed variance, then we're going to describe as gamma distributed. So it's got a couple of parameters. And reminder here, make this a little bit bigger. So what we're looking to do is this functionality right here, gamma, where we've got n minus 1 over 2 and n minus 1 over 2 times this sigma squared marginal. So that's what we've got going right here. So we've got our gamma. So the A var and the B var parameters need to correspond to these two components here. So we've got our A var here is right here. So there's our n minus 1 over 2. And down here we've got our, well, the equivalent of n minus 1 over 2 times sigma squared marginal, but we're writing it in terms of a precision instead. So this tau marginal is simply the reciprocal of that sigma squared marginal. So we're multiplying it instead of dividing it here. So that takes care of that. We don't need to introduce any new parameters in order to model then the sample variance. And I'll just point out a couple of things here to get our so-called individual predictions. Again, individual in this context will mean an individual treatment arm, not an individual patient. We simply repeat the likelihood statements that we had above, except we're changing the name on the left-hand side to something which is not in the data set. So we're doing simulations, which are now going to be conditioned on the arm-specific random variables for these. And then if we want to make what I've been terming population predictions, where we're predicting new observations in a new trial, or to be even more specific, we're going to predict a new observation in a new trial that has exactly the same design as the ones that we were analyzing, so that we can use that for doing some, use both that as well as the individual ones for some model checking. So again, we're repeating what essentially looks like the likelihoods, except I noticed some of the quantities here are now modified with a different name where I stuck a pred on them because they depend on some of those random effects. And some of those components then have to be recalculated. Anything that depends upon any of the trial any of the arm or trial specific random effects needs to be recalculated to contribute to our population predictions. Okay, that's pretty much that story. Actually, before I go ahead and show the results in that, wanted to see if there's any questions at this point. Okay, I'll keep my eyes open here. In the meantime, let's take a look at the corresponding R script that we'll use to run this. Okay, most of this is old news on the top here, just all the usual bookkeeping. Let's see. There's now one thing I probably suggest you take a look at is some of the bookkeeping that's done here to deal with the fact that we've got 3 levels of random variation instead of 2. Some of it ends up being a little bit messier as a consequence of those 3 levels of random variation. So you can see the first part here is just pulling in the data set itself. But I need to create some of those indexes that are referenced inside the bugs model. We have to create inside here. So that's where you see some of these components. So we've got a study ID. So we need an identifier that's an integer sequence starting at 1 in here. And so that's being created with the line you see here. So there was a study identifier in the original data set, but it wasn't necessarily a simple, unbroken integer sequence, which is what we need. Ditto for the unit ID, that happens to correspond with the thing that was referred to as NMID, turns out to correspond to an identifier for each of the treatment arms. So those are the main indices. In addition, I need to, and these are, I gotta remember to say this correctly here. So the first ones here are basically we're going to be telling the bugs model which study ID and arm ID correspond to a corresponding observation. But in addition, for some of the bookkeeping I was doing in the model, I have to be able to tell. Okay, this thing's acting funny. There we go. I have to tell the bugs model which treatment arm. So let's see, we got to keep this straight. I need to tell it, which one is this? This is study. Yeah, I need to be able to tell it what study ID corresponds to a given treatment arm. And that's what's going on with the values I'm constructing here. So that's where I'm getting the appropriate study IDs for each one of the treatment arms. And then this is also telling it, this is also taking the, where am I going? Yeah, this is taking the sample size and telling it the corresponding sample size for each one of the treatment arms. Let's see, we're not actually using that covariate, so don't worry about that one. So this is just creating all of that. I'm trying to see if there was anything I really wanted to point out here. Most of it's fairly straight ahead. I'm telling it how many trials there are, how many treatment arms, how many observations. This is our number of patients per. This is the number of patients corresponding to each one of the observations. This is the number of patients corresponding to each one of the treatment arms. Study, that's the study ID corresponding to each observation, and study unit is the one is the study ID corresponding with each arm. Unit here is referring is the identification corresponding to a given each treatment arm. Time is pretty much self-evident. Dose, ADAS-CFB, that's our ADAS-Cog change from baseline, and then we have our sample variance for our ADAS-Cog change from baseline. And these two quantities, well, the one, the T star, is a parameter associated with our truncated Emax reparameterization, and dose ref of 5 milligrams per day is that reference dose we were using for donepezil. Let's see, I don't know if I want to go through, I probably don't want to go through these in detail, but you'll see a couple of little tricks being done inside my initial estimates function. As I usually do, I generate initial estimates, different initial estimates for each chain by some random sampling. And I'm introducing truncated normal distributions for some of these, for where I want to generate initial estimates in cases where I've used something like a uniform distribution for the prior distribution, so that I don't accidentally create an initial estimate that's outside the range of a given parameter. If you do that, you'll just get an error. So that's why I'm introducing those. So as you look down through here to see some of the initial estimates that are given here, you'll see things like this, where I've used that truncated normal distribution to generate an initial estimate, in this case for the gamma, or the exponent associated with the dose response component of our drug model. And you'll see that sort of thing used in a number of cases throughout here. Okay, all the bookkeeping around which parameters do we want to keep, which ones do we want to plot, various predicted values and stuff for our model diagnostics, and then our model run down here. One thing that I believe is different from the version I distributed to you, again, as I changed clear working directory to false and debug to true in here, because that's generally my preference, at least for early runs of models. Not too much to say about the rest of this. It does the usual posterior predictions, both individual and population predictions, and I spotted an error in the code. I'll have to post up the revision. It's somewhat minor error. Sorry, let me scroll here. So the first part of this, I do the individual predictions, and those look fine. But when I do the population predictions, what you'll notice is in this section is when you go down to right here, where I create the title inside the plot. You'll see in the version you've got right now, it says individual predictions when it should say population predictions. So that's the only thing. So it still runs, it's just that the labeling is incorrect. Okay, so I'm not going to tell you too much more about that. Let's just go ahead and run it. Let's see if I got an R thing open. I guess I do. So let's go ahead and run it. This isn't too awful. It requires about 2 to 3 minutes to run. So I guess we can probably tolerate that. That's quite a bit less than what it took to run the it takes to run the full 8-ASCOG model that I did last week. And this is also a good opportunity to ask questions if you have any, since we're going to be watching paint dry for a couple of minutes here. The one thing I did not get time to do that I alluded to actually at the end of the last class is I wanted to do some population simulations based upon this model just to illustrate it, because we do have the complication here of having an additional level of variation to incorporate into that simulation. So I'm going to try and carve out some time between now and Wednesday to see if I can do that, or if at the worst maybe by the following Monday, but hopefully by Wednesday, just to illustrate that process. Basically, we're getting into a model that where the simulation should be done in a manner comparable to what I lectured about, where you're simulating from models that have inter-individual variation components as part of them. Since essentially that inter-arm variation is kind of you can think of that as sort of being a manifestation of inter-individual variation in the summary statistics. What did that take? Oh, it erased it before I could see. I think it only takes around 60 seconds to do every 1,001 of these iterations, but it does seem longer than 60 seconds. In fact, while it's wrapping up, maybe I'll mention, I think I'm probably going to change the order in which I do some of the presentation. Instead of going into modeling other types of summary statistics right off the bat, I think what I may do instead is jump to, where'd we go? I need to think about this. I may jump into talking about combining summary and individual data. Actually, I haven't locked in and decided that yet for sure, because there actually isn't a lot of lecture material. I end up illustrating this pretty quickly with well, originally I was doing this with a hands-on example, but I might do an example in class initially for dealing with that. Main reason for probably not jumping right into the other types of summary data is I'd like to actually develop a little bit more material on that before we actually do it. So tentatively, we'll be talking about bringing in data. Oh, I see that's done. Anyway, talking about combining individual and summary data. Okay. Looks like that's finished. So let's go ahead, and it seems to have finished successfully. Let's let it do its plots. Okay, it's starting to move stuff over there. Okay, well, it's continuing to make plots here. Let's take a look at the history plots. So here we've got history plots for a number of the parameters here. Some of them are fuzzy caterpillars, some of them not quite so much. In particular, you can see both the E placebo hat term and the E delta hat though all three chains seem to be bouncing around pretty much a common value, so I'm not too worried about convergence per se. There's still a fair amount of autocorrelation apparent in those, suggesting that for things are behaving reasonably well, but for production run, I'm likely to want to do more samples. Same thing is true for omega drug here and gamma, ET50, E star. So again, nothing terrible, but not quite enough for production work. Yeah, same thing here for the other omegas. So, I think if we do something on the order of around 10 times more post-burn-in samples, probably in fairly good shape. We can confirm that hypothesis, well, at least partially confirm it by taking a look. Actually, let's open it so I can make it bigger here. If we look at the effective ends for these, we can see, though, a number of them aren't bad. Now, keep in mind, let's see, we did what? We did, trying to remember how many. So we did what? So we would have ended up 10,000, so we would end up 5,000 post burn in per chain, but we're only going to keep every fifth, so we'd have 1,000 remaining per chain, so we should have 3,000 samples out of this. And those 3,000 samples, you can see for some of the parameters, we end up somewhere on the order of 1,000 effective, an effective sample size of around 1,000. But we also end up with a few that are substantially lower, the worst being this omega E placebo study component. You can see here it was struggling a bit with that. So, depending upon which parameters are more key to any inferences, I'm likely to want to do, just as an eyeball here, on the order of 10 to 20 times more post burn-in samples for a full production run. Let's see what the rest of this looks like. Okay, just a look at our various marginal distributions here. Again, on these things, most of these actually don't look that bad in spite of the autocorrelation. Some are, you can start seeing some that are a little high, like the gamma is still not quite settling down close to 1 here. But I think the history plots largely tell the story along with the effective N. Here we've got our individual predictions here. Again, I probably need to use smaller symbols or something here so you can see a little bit better how the predictions compare with the observations, but for the most part, there's reasonable agreement. Okay, this is the same ones, but looking at blowing up the first 12 weeks just to get a better look at what's going on during that period. Let's see, those were oh, sorry, I just realized I was jumping past this. So this is the mean. This is the standard deviation in here. This is, again, the mean, but just for the first 12 weeks. And here we've got the standard deviation for the first 12 weeks. Most of them pretty good with a few exceptions here. You can see that one we had shown earlier, which seemed kind of odd, as the model doesn't pick up, and there's something a little bit systematic going on over here. And these are the population predictions. The inter-arm variation in the slope, well, actually both the inter-arm and inter-trial variation, the influence of that starts becoming apparent when you look at these long time frames for the study here, which goes out to 3 years. You can see that you end up with this thing kind of fans out an awful lot, perhaps unrealistically so. Standard deviation seems a little cleaner actually. And again, looking at it blown up for the first 12 weeks, first 12 weeks looks generally cleaner. And the rest of this is just some diagnostics for some of our random effects in here. Wasn't planning on going over those. Okay, we're approaching our 3. I'm trying to think if there was much more I really wanted to say about the example we just had here. Probably nothing immediately coming to mind until I do some of those simulations to illustrate use of the model. So I guess let me just stop here, see if there's any last comments or questions. Okay, doesn't look like anything's popping up here, so guess I'll look forward to talking to you again on, I guess, this Wednesday. So bye for now.